Good morning, everyone. My name is Kuan-Hao. I'm a second year computer science PhD student at Johns Hopkins University. So today it's my pleasure to present my work collaborating with Dr. Langmead at Johns Hopkins University, and also Pei-Wei, Chen and Dr. Sanjit Seshia at UC Berkeley. So the topic I'm going to cover today is called Wheeler Graph Toolkit, WGT, tools and algorithms for recognizing, visualizing, and generating Wheeler graph. So back in 2005, Ferdinand and his coworker designed the XPW transformation of the tree in the spirit of the Wheeler transform. So this transformation contributed the first non-succinct representation and manipulation of the label tree. So given a label tree, you can come up with a two-array by sorting the edges and the path in the graph. So this is the core idea of the XPW transformation. Sorry, that technical. Then in 2012, Bo and his colleague published a new succinct different graph representation. So this data structure is known as faults, which is used as the initial characters of each of the four other span faults. So on the left is the third order different graph, and on the right is the succinct different graph representation, which F stores the tally of the array, and the W column stores the outgoing edge labels. So the core idea is also sort by edges. And then we can also introduce the finite automata idea into the graph. And then in 2014, Sarin and his colleagues introduced the general contrast suffix array, which is known as GCSA. So given the multiple sequence alignment, we can build a finite automata out of it. And in this example, it's the reverse deterministic graph. We can use the prefix styling algorithm to unzip the graph and make it prefix sorted. So this is the idea of it is also sorted by the prefix. And then in 2017, Sarin combines the idea from the original GCSA and succinct different graph and proposed the GCSA2. So some optimizations are introduced, for example, like reduce the memory requirement and also extend the functionality of the acronym text. And one of the important applications is the variation graph. So here's an example of a variation graph on the chromosome 9 subternary region of yeast genome. And there's another very important application, which is HiSet2. So HiSet2 is the first practical graph-based read aligner combining the GCSA with the HiSet read aligner. It was developed by Dylan King at Johns Hopkins University as well. So given the reference sequence, we can incorporate the SNPs into the graph, and also use the prefix doubling approach to prune the graph and make the graph indexable. So all the data structure that I talked about are all variants of the Wheeler transform and their application. In a 2017 paper, Gatti, Mazzini, and Sarin presented a unified perspective on variants of Wheeler transform. So interesting, they arrived at a uniform representation of all this data structure. So basically, we can summarize the Wheeler graph into three rules. So if a graph with these three rules, it has the perfect properties of the Wheeler transform. So now it comes to the point that now we have a well-defined mathematical rules and a unified framework. So it will be interesting to understand more and try to come up with some data structure and also how to index the graph. So this is our contribution of our work. First, we proposed, we developed a visualizer using a bipartite representation, so you can visualize a Wheeler graph and have a better understanding of it. And we also implemented the first Wheeler graph recognizing algorithm, which we call the recognizer. And we also have the generator. So first, I'll talk about our visualizer using a simple example. So given the DNA sequence T, first, we can write out all the prefixes of this T. And each of them represent a node. For each node, we label the incoming edges like this as the last character of the prefix. And then we can push the node all the way to the right and sort and color the edges by directions because originally when we do the pattern matching, it's backward search. So if you sort in that direction, then it's going to be the forward search. So now this ordering is the sorted order. The graph now looks a bit messy, so let's look at one color edges at a time. So for these three nodes, they have incoming edges labeled as A. And for this node, it has incoming edges labeled as C, and G, and T. So you can see that the incoming edges group together, and now we move the sorted order back into the node, and put the node back to their original order. So this is the weighted graph representation of this linear sequence, DNA sequence. I just put it horizontally so that it'll be easier to show the visualization result. So the sorted, basically we can think of this sorting method is just like relation form. It's just like we flip the prefix and also we did the sorting in a graph. So first we can duplicate the nodes into two rows. The first row represents edges, the node that having edges going out, and the second row represents nodes having edge going in. So basically we can change the representation to simply move the edges going out from the first row and go into the second row. So now I'll put the nodes back to their order. So, one thing to mention is that nodes in the same column that represent the same node. So first is 0, and 1, and 2. So I'll after finishing the A group, and then C group, G, and finally T. So this is the bipartite weighted graph representation that our visualizer will open. So using this simple example, I will introduce the definition of weighted graph. So there are just three simple rules. The first rule is that node with integer 0 comes before every other node. So one thing to mention is that it's not necessary to have exactly one. It's possible to have none of them or more than one. And for the second rule, you need to check every pair of edges. So I put two edges here so it's easier to understand. In this example, if A plum is lexicographically bigger than A, then the destination node, B plum, needs to be bigger than B. So in terms of graph, here, for the C group, since it has incoming edges labeled as C, it's lexicographically bigger than A. So all the nodes here, the order needs to be bigger than any of them. So basically what it tells us is that we can simply group nodes into beings. In this example, there are 4 beings, A, C, G, and T. And the third rule is that if A plum is lexicographic is equal to A, so that means that they're in the same group. So if the origin, the source, is bigger, U plum is bigger than U, then the destination 2 must be bigger or equal to 1. So what it tells us is that edges with the same color, they cannot overlap with each other. So we can check the C group, G group, and T group. So this is our visualization representation of showing this is a weighted graph. So it provides us an easier and cleaner way to see if a given graph is good strength. Move on to our second contribution. We also implemented the first weighted graph recognizer. So here I use a potential application of weighted graph to introduce the weighted graph recognition problem and our recognizer algorithm. Before I show the example of making a linear DNA sequence into a weighted graph. So if we want to index this multiple sequence alignment, one intuitive way is just we can use a degree graph to index it. Or maybe you can use a TCA reverse deterministic graph that I made in the previous example to index this multiple sequence alignment. So I'll dive into the degree graph first. So this is a multiple sequence alignment. We can first remove the gaps and also append the $ sign at the end of the alignment. And then we take K-equal and break the sequences down into dreamers, and so on and so forth. We add edges. And now we collapse the node having the same dreamers. So genome coordinate, one of the problems of the deburring graph is that the genome coordinate are collapsed. And I simply just label the edges. So for edge label, incoming edge label, we label it as the first character of the node. So this is the graph are all weird graphs. However, it has a drawback of genome coordinate are collapsed. So what about the reverse deterministic graph? The good thing is that it preserves the genome coordinate. However, it is not always weird graph. So I also go through a simple example to show how to build the reverse deterministic graph. So we first add the dollar sign and the pound sign, and we process following the arrow direction. So we can create nodes, and we find the previous ungapped node and the edges there, and T and C. So note that for this A, since there are gaps here and also a C here, so we create a C here and add the edge. And since there are gaps here, so we also need to link the edge all the way to this C and this G, since there's also a gap here. So this is our reverse deterministic graph. And the reason why it's called reverse deterministic, that look at this A, for example. If we check offstream, we can only find one T. So it's deterministic. And you can check all the nodes. So basically, we can only find one node having the only label of that A, C, or G. However, if we go downstream for this A as example, you can find this C or this C. So this graph is not forward deterministic. And I simply label the edges by the labels of their children. Now the question is this edge label graph a weird graph? And this problem is defined as the weird graph recognition problem. It turns out that this is a pretty hard question. One of the main contributions of our work is that we create a recognizer to recognize, given an edge level graph, to tell the answer if it's a weird graph. And here I'll just tell you the answer. Yeah, this is not a weird graph. However, we can fix it to unzip some of the node into bubbles and actually turn this graph into a weird graph. So this is the weird graph ordering of this reverse deterministic graph. So now we've seen two ways of building a weird graph from a multiple sequence alignment. We can either build some green graph, however it ends up with a graph with 18 nodes and also 21 edges. We can also go through another path and try to fix it and make it into a weird graph. And in this case, we got the graph having 14 nodes and 16 edges. So depending on the case, the green graph might be bigger than the GCSA. So it has some potential of how to fix it. But before we fix it into a weird graph, the first step is at least we need to understand if the given edge level graph is a weird graph or not. So now we go back to the weird graph recognition problem that I just mentioned in the GCSA example. So given an edge level graph, is it a weird graph? I just simply put the rules here so you can easier to see. So we can start with some random ordering and check every pair of edges. So for example, let's check these two edges. Since A is lexicographically smaller than B, we can use the second rule. So the destination 7 needs to be smaller than 3, which is a conflict. We can simply swap the order of these two nodes and fix this problem, and iterate and go to the next iteration to check the next pair of edges. So if we can find just one or more than one, if we can find an ordering, then it is a weird graph. And if we try all the possibilities and we cannot find a proper order that fulfills those three requirements, then this is not a weird graph. And it turns out that we actually can find an order in here. So this is a weird graph. And we can further use our visualizer to check if the ordering is the weird order. So for example, this node with integer 0, it comes first. And also these three nodes having A as the incoming edge label. So the A, they're here. And also with the incoming label, C is here. So basically you can see that node chart grouped into three things. And also edges with the same color, they do not overlap with each other. So this is a weird graph. And it turns out that weird graph recognition problem is pretty hard. It's in general and incomplete. So in this work by Gibney and Dankishan, they propose a state-of-the-art weird graph recognition algorithm, which I will call GNT's algorithm in the later presentation. So the hardness of weird graph to recognize if it's a weird graph is largely controlled by this parameter D. So the definition of DNFA it describes a weird graph where all nodes have bigger or equal outgoing send level edges, and at least one node has exactly the outgoing send level edges. So for one NFA, the linear sequence, we can always create a one NFA, which is the example that I made. And also try the green graph, they're all one NFA. And there's some harder graph, for example, if t is bigger than 1, it's harder to recognize. And in the previous example, this graph, this node has 2 edges labeled as A going on, so this is a 2 NFA. So now we understand the hardness of weird graph. So in order to understand GNT's algorithm, first I'll introduce how to encode the weird graph. So this 3-bit array encoding approach is proposed by Mazzini and Sarah in 2017 as a paper. So a weird graph can simply be encoded into a very compact data structure, 3-bit array data structure, using the bit array O, L, and I. So the bit array O represents the alt degree, L represents the label, and I represent the in degree. So take this node for example. This node has 3 edges going out, so the alt degree is 3. So we write off 3, 0, and 1 as a separator. In terms of label, it's A, A, B, so we write them off in order. And the in degree of this node is 0. There are no incoming edges, so we don't write any 0 and the 1 as a separator. So we can go through the weird graph order of the node and write off the 3-bit array. And the 3-bit array, the length of O is E plus N, and I is also E plus N, and L is E times log sigma. And here's the pseudocode of GNT's algorithm. For GNT's algorithm, basically, we need to iterate through all possible encoding. So take O for example, the length of O is E plus N. So for every position, we can select either 0 or 1. So the number of times that we need to check is 2 to the power of E plus N. So because we need to check all possible encoding, so this is the total search space that we need to go through. And inside the for loop, for every encoding, we need to check if it defines a valid weird graph. And if it does, then we undirect the G-plum and also undirect the given graph G, and check if these two undirected graphs are isomorphic. If they are isomorphic, then it is a weird graph. But if it's not, then it is not a weird graph. But actually, this problem is in an inner loop, like graph isomorphism check, can be computed in a sub-exponential time. So basically, this algorithm is bounded by the first for loop. This is the time complexity of this algorithm. It's exponential on E and E times log sigma. So now here comes to our algorithm. We developed Willy, we call it Willy. It's our weird graph recognition algorithm. And Willy is composed of 2 parts. The first part is Green-Hemming heuristic. And the second part is the solvers. So first we use Green-Hemming heuristic to trim down the searching space. And then we pass those ambiguous node ordering into the solver. In Willy we have a permutation-based solver, which we call the Willy PR, and also the SMT solver, which we call Willy SMT. So here I just simply move the nodes in the graph and put them in 4 different levels. With the first level, start level, have no edges going in, and the A level have edges labeled as A going in, and B and C and so on. So by the second weird graph rule, we can simply group nodes together, right? So in the A level, the range of nodes is from 2 to 4, and B level is from 5 to 6, and so on. So the first step is to label with the maximum possible value. For A group, simply we just label all nodes with 4, and here these 2 nodes label 6 and 8. So we start the in-node list sorting. So in-node list is the new idea that we propose in the weird graph toolkit this paper. So what it means, let's take this node for example. For this node, it has 2 nodes coming in, and this node is currently labeled as 1. So we write 1 here, and this node is currently labeled as 4. So we write 4 here. So the inner list of this node is 1, 4. And we can do the sorting based on the inner list and do the relabeling. So now it turns into 2, 3, and 4. And one thing to note is that it's not always sortable. In this example, it's a good example, so now we can like break the ties and reorder the nodes. However, it's possible that we have the same inner list, so we cannot break the tie. So we're gonna just put them in their current label and move on to the next label. And after we check through all different labels, we'll come back and see if we can use the new label that we got to break the tie that we have. Another possibility is that this is simply just not a weird graph. For example, like here, 1, 4. 4 needs to be smaller or equal to 6, which is constrained by the third weird graph rule. So if we do the end-of-list sorting and we found that, okay, here we got a 9 here, then there's a conflict. This is not a weird graph. So for this example, we simply can get the order and move on to the B level and do the sorting again, relabeling, and see. So now, as I just mentioned, we're gonna, after we go through, this is actually a for loop, so after we do the inner list sorting, we'll go back and check again. And if all nodes are stable, then we're gonna see if every node has their distinct, we'll check if every node has distinct order. If so, then this is a weird graph. But if it's not, then we're gonna pass to a solver, which we have really PR and also really SMT. So here's a quick recap of our recognizer. We provide a permutation-based solver, which we call the Wheelie PR, and also an SMT-based solver, which we call the SMT. Now I'll move on to our third contribution, which is the weird graph generators. So we downloaded 25 DNA and amino acid multiple sequence alignment using the Genco REST API, and use our generators to generate random weird graph, green graph, and tries. And all these three different graphs, they're all weird graphs. And we also use the generator to generate the pseudo-degree graph, which is the degree graph that we should not do the Kimmer-Slawski, and also reverse determinacy graph. So for this graph, the x-axis is the log runtime of GNT's algorithm. And the y-axis is the log runtime of really PRs of really PRs. So let's look at this first group and every node here represents a graph. So now let's look at the first group of the dots. For these dots, we can see that really PR can solve all of them in a pretty short amount of time. Basically, it's just between 100 to 1,000 microseconds. And for GNT's algorithm, basically, it takes quite a long time, all the way to 30 seconds. So this node, for example. And for a second group of graphs, for these graph sets, basically, GNT's algorithm cannot solve them given the 30 minutes time frame, whereas the Wheelie PR can solve all of them. And for this part, for these graphs, basically, GNT's algorithm and Wheelie PR cannot solve them within a given time period. And this is the interesting part. So we further use our visualizer to see where these graphs are harder to solve, and it takes more time for the algorithm to solve. So it turns out that these graphs, they are DNFA with D bigger than 1. For example, like A, it's a 2NFA because it has 2 edges going out. And this is a 2NFA with 2 edge label. This is a 2NFA with 3 edge label. And this is a 3NFA. So, as I mentioned in the previous hardness of the recognizing weird graph, this is controlled by the parameter D. So now we have to ask ourselves the question, is it possible that we can do better? So that's why, with the inspiration from the application of the Boolean satisfiability formula to solve the special cases of the recognition problem, which is mentioned in this paper, read by Langmead and his colleagues. So we hypothesized that SMT method, the satisfiability module theory solvers, can actually use to solve all or part of the weird graph recognition problem. So SMT solver is a combination of the SAT solver and the theory solver. So input to the SMT is the formulas that the problem that we want to solve. For the weird graph example, is the 3 rules of the weird graph. And all are going to be the assignment of the variables a Python implementation of the SNT. So basically, it's very short. As you can see that recognition is a very hard problem. However, we can just simply use a few lines of code and actually encode the problem and feed into SNT. So I put the rules here and also visualizer here. The first rule is no with integer 0 config for every other node. So basically, just 2 lines of code, we can encode the problem into the SNT. And the second rule basically says that we can group in, and the third rule basically says that edges cannot overlap cross each other. So this is a weird graph, how we encode the problem into SNT and feed into the SNT solver. So I introduced the renaming heuristic and the SNT approach. You may wonder, like, we already have such a powerful SNT approach tool, and why do we still need renaming heuristic? So here's the result that I simply found really SNT, which is the combination of the renaming heuristic plus the SNT solver, and also purely encode the problem into SNT and feed into the SNT solver. So here's the result. This is the practice plot that is widely used in solver competition, and here you can see that. So basically what practice plot shows is given a set of problems that we want to solve and given a period of time, see how long it takes for both solvers to solve the set of the problem. So for really SNT, basically it can solve everything very, and this is an accumulated time plot. So basically really SNT can solve all of them with a very short period of time, whereas the pure SNT, when the graph gets bigger and more complicated, it's harder to solve and take way much more time. And this is the experiment on the green graph, and this is the experiment on the reverse deterministic graph. So the conclusion from this result is that with the help of some human intuition to encode the problem into a renaming heuristic, we can get way much better result. And as I mentioned, the weird graph recognition problem is largely controlled by D. So we changed the D for various of graph, and for each set of experiment, we tested on 20 different graphs. And the blue lines show the result of really SNT, and the orange line shows the result of really PR. So what we can see here is that when D is small, before 1, 2, or 3, basically both solvers can solve very efficiently. However, when D gets bigger, really PR has a problem to efficiently solve the problem, like given a period amount of time. Whereas SNT is a more stable and efficient solver to solve the problem. So here's the conclusion. We implement the first weird graph recognizer, which I would recommend you to use the renaming heuristic plus the SNT. And also we provide the visualizers and also generators to generate random weird graph, try the green graph, and reverse deterministic graph. And the main algorithm part is the recognizer. And recognizer is effective up to graph with 4,000 nodes, 20,000 edges with 5 edge level, at around like 1,000 seconds. So I want to thank the co-first authors of this paper, Pei-Wei, Chen from UC Berkeley. This is the one who proposed the idea of using SNT to solve this problem and make our recognizer very much more powerful. I want to thank the project advisor, and Sanjit, Seshia. Especially want to thank Ben. This project started as a final project in his course, and he gave me a lot of great input, and now it becomes a RECOMB paper. Last, I want to thank my PhD advisors, Dr. Stephen Salisbury and Paul Kuan-Hao for their great support. And for that, I'm happy to take any questions. Thank you.